Let us discuss this result. This is very important result. See, this result gives how to find total derivative with the help of gradient. See, already we have seen the procedure of finding total derivative. Few examples also we have solved in previous videos. See, if the procedure is little bit lengthy, we define the function, getting after that we find linear transformation using epsilon delta definition. So instead of that, I think using this result we can easily find total derivative of any scalar field. So let us discuss this result. See, this result says that function should be differentiable. Obviously it should be differentiable, then only we can find its total derivative. And the second thing, gradient of f at a should exist. So if f satisfies these two conditions, we can find total derivative of f getting at a. T means total derivative, or we can write in this way also. Gradient of f of a dot h. So using this formula, we can find total derivative of given function at a given point. Let us start to discuss its proof. So f is differentiable at a. So this is a given information I have written here. So the function is differentiable implies directional derivative of f exists, okay, in any direction u. So that thing I also mentioned here. So let us start now. So let e1 is equal to 1 0 0 0 0, e2 second component is 1, remaining are 0, and so on, en, that means all components are 0 except last one, which is 1, b standard basis, this standard basis of Rn. So I hope all of you are familiar with this basis in paper 2, okay, linear algebra. You have already seen this is the standard basis of Rn, okay. So let H belongs to Rn. H be any elements of Rn I am taking here. H is required here, right? So that's why that H is I have taken here. So then H, any element of Rn. So it will be like this, H1, H2 and so on, Hn, right? So this is equal to, I can write H1, all elements are 0, plus second element is H2, all elements are 0, plus and so on, 0 0, and the last one is Hn. If you add, obviously H1 plus 0, we will add first component, H1 plus 0, all remaining are 0, so we will have H1 first. Similarly 0 plus H2, all entries are 0, so we will have H2. So simply I express this H in this way. After that I am taking H1 outside common, so here 1 0, remaining are 0. Here I will take H2 outside, so we will have 0 1 and so on 0. And here obviously what will I do? I will take Hn outside, 0 0 and so on 1. Getting the point? So 1 getting. So if you multiply again, it's a constant. If you multiply again, you will have a previous step. So this is equal to H1. This is nothing but our basis element E1 plus H2. This is nothing but E2 plus and so on. Obviously the last one is Hn and this one is En. So in this way we express H as a linear combination, okay, of E1, E2 and so on, En. After that I am going to apply linear transformation, this linear transformation now, which is a total derivative of both sides, okay. So make a screenshot of it. After that we will go further. I have operated T on both sides. T means total derivative here, okay. But T is also linear transformation also. So you know that in case of linear transformation, if addition is there, we can take separate, we can operate separate T. Getting, as well as if there are any constants, we can take them outside. So let us do all these things here. So H1 T of E1 plus H2 T of E2 plus and so on Hn T of En. But see, basically T is nothing but total derivative of f at a. Getting? So that's why I am going to replace T means df of a of h. Since T is a total derivative, but total derivative of f at a we can write in this way also. So here everywhere also I should replace it. So this is h1, getting h1 d f of a e1 plus h2 d f of a e2 plus and so on hn d f of a en. See, few days before we have discussed one result, if you remember, okay. So that result was, I will mention here, d f of a of u, that means total derivative of f at a in a direction, okay, at u is equal to directional derivative of f at a in a direction of u. So this is a very important relation we have already seen, okay, in our previous video. So let us use this thing here. So simply, symbolically, what we have to do, whatever inside in second bracket you have to write as a suffix of d, okay. So it is actually relation between total derivative and directional derivative, getting. So see, using this relation, tell me what can I write here. So this is equal to h1 d, that e1 I suppose to write here, e1 f of a, h2 here what I write, d e2 f of a, and so on, hn d en f of a. Simply I use this result which we have already proved, getting. See, now we have a directional derivative here in a direction of e1, directional derivative in the direction of e2, directional derivative in the direction of en, but even e2, en, these are standard bases, that means these are standard axes, getting. For example, in three-dimensional you can take any vector, okay, and you can find directional derivative, but we have a standard directions along x-axis, along y-axis, along positive z-axis, you are getting. So that means e1 is nothing but directional derivative in a direction of x-axis. But we have a separate symbol for directional derivative in the direction of x-axis, that is nothing but dabba f by dabba x, partial derivative of f with respect to x. Directional derivative in a direction of positive y-axis, that is nothing but dabba f by dabba y we have, and similarly for z, dabba f by dabba z. So here also I can write, so this is equal to h1, this is nothing but dabba f by dabba x1, getting, of a. Since in the direction of e1 standard axis, getting, and here h2 dabba f by dabba x2 of a, and so on, what can I write, hn dabba f by dabba xn of a. So I can mention here, because directional derivative in the direction of ei, that is nothing but dabba f by dabba xi of a. So I wrote that thing. After that, what will I do? I can write in this way also, dabba f by dabba x1 of a, dabba f by dabba x2 of a, and so on, dabba f by dabba xn of a, getting, into h1, h2, and so on, hn. So that means in a form of dot product I have expressed. So you know how to solve dot product or inner product also, you can say. First component into first component plus second component into second component plus third component into third component, and so on, last component into last component. So same thing we have, simply I express it a different way, right? So have you seen it anywhere? This is nothing but gradient. This is nothing but del f of a dot, and this is nothing but our h. So in this way we proved the total derivative of f at a is equal to gradient of f at a dot h. So in this way we completed the proof of this theorem. Okay, make a screenshot of it. After that we will stop. Thank you. Bye bye.